Okay, you're hooked. Join the cool crew and write equations with Greek letters like that. No, that is too cool. I could never go there. Come with me, my friends. Okay, so before we get into the cool equations, we need to develop some comfort with radians. And we're going to start with this question. If you go halfway around a circle circumference, how many degrees is that? And I need everybody to agree that the answer is 180 degrees. Then we ask, how many radiuses or radii long is that half circle of arc? How many times does the radius fit into a half a circle? And I need everybody to agree that it goes in pi times, that the radius goes into a complete circumference 2 pi times, into half a circle pi times. So what we're doing is, instead of measuring angles in degrees, we're going to start measuring angles in what are called radians, which is a term that means we're going to measure the angles in terms of radii. We're going to see how many times the radius fits into the arc that is subtended by the angle. So we had this half circle, there's its center, and if you take this radius and lay it out on here, it goes a little bit more than 3 times into that. And so we say 3.14 radiuses are how long that arc is, and that's what we're going to say the angle is. That 180 degrees is going to be the same as pi radians, and that's what radians are all about. And you've probably worked with them so much that you're very comfortable with them. But it is an issue because we're going to do everything in radians from now on. So, how many radians is the angle of a half circle of arc? This is not a trick question. It should be insultingly easy. How many radians is equivalent to 20 degrees? And I, because I grew up speaking degrees, always have to translate from radians to degrees before I understand. I do not dream in radians, that if you say, here's this angle and it's this many radians, I first have to figure out how many degrees is that before I know what you're talking about. And how do I do it? I do it with this correspondence, that 180 degrees is equal to pi radians. So 20 degrees is 1/9 of 180. And there we're done. Okay, I've got a circle. This is the diameter, not the radius. And it rotates around 1.5 times. So how many radians has it turned? Well, think about a point on the edge of the record. This was a way people used to listen to music. They would have these great big plastic things, and they would make music for them, and they would turn around and around, sort of like a disc, except it was out where you could see it with your eyes. If this point goes around 1.5 times, how many radians is that? Then, to get to this question here, consider this, that we have defined the angle in radians it's an A, to be equal to the length of the arc, and we often use an S for that, divided by the radius. How many times does the radius fit into that arc? Well, using this then, you ought to be able to answer this question. Now we're going on to a discussion of rotational motion. Finally, all the geeky Greek letters come into our life. Translationally, that is, to translate is to go from one place to another. To go from French to German, that is a translation. To start one place and end in a new place. But rotation, you don't go to a new place. You stay in the same place, you just change your orientation, your angle. So instead of traditional displacement, delta x, we now have angular displacement, which is going to be delta theta, and it's going to be measured in radians instead of in meters, as was the case here. And then you take the rate of change in the displacement, the rate of change in position, or the displacement divided by time, and that's velocity in meters per second. And similarly here, we will take the rate of change in your angular position, your angular orientation, and we'll call that angular velocity. And the symbol we will use is an omega. Not a W. Make sure it's nice and curly when you make it. It's not a W, it's an omega. It's actually a lowercase omega. As many of you may have encountered an uppercase omega in various commercial products or in religious symbology. It is the last letter of the Greek alphabet. So that when you say this is the beginning and the end, you say this is the alpha and the omega. That's a capital omega you see there. This is a lowercase omega. This looks very, oops, that's a T. Ay, ay, ay. That's a T there. This would be the angular velocity. And we have changes in the angular velocity. Well, changes in the translational velocity, which we called acceleration, which would be in meters per second squared, and here we have angular acceleration, and we use a Greek A. This is evidently the closest they could come to a V in Greek, and they didn't even try to go for an X in Greek. We just like theta for angles. But this is like an A, a Greek A, an alpha, and it's going to be equal to exactly parallel to that. It's going to be equal to the change in omega over, and that's a T again. I'm sorry. And it would be in radians per second squared. And we go on. What we need to do is to not get freaked out. We're talking about the same ideas we've already been talking about for several months. We're just using Greek letters. But it's really the same thing, and it behaves itself so nicely that the ratio of the resistance to changes in motion, this quantity m, which was inertia, has a corresponding rotational inertia, which is also sometimes called the moment of inertia. What exotic language! But we're just going to take the rotational equivalent of force and divide it by rotational acceleration. Well, I need to introduce to you that the rotational equivalent of force is called a torque. And we're going to study torques later, so I'm not going to get into what a torque is, but it's equivalent to a force. It's what causes this acceleration rotationally, and that ratio is equal to this quantity that we call the rotational inertia. The units are goofy. I do not pretend that this is nice. They are kilogram meters squared, and I'll show you why another day. Momentum. We've just been talking about momentum. Well, here we are. You have translational momentum and angular momentum. What would you guess the formula for angular momentum ought to be? It would be the angular equivalent of m and the angular equivalent of v multiplied together. The symbol for angular momentum is a capital L. Sometimes a lowercase l is used. And it's equal to the rotational inertia times the rotational velocity. Finally, and I hope this will comfort you, here are a whole bunch of familiar equations that you work with and feel very comfortable with, I hope. Please write down what you think their rotational equivalent would be. Stop the show, write down what you would guess the rotational equivalent of these three equations would be. Now, start the show again and see if this is what you got. Just replace the delta x by delta theta, the v by omega, the a by alpha. Boom! There it is. There's your hook. Oh, I feel so cool! I can write that, and it has meaning for me. And it works. It is correct. This one here would become omega final squared is equal to omega initial squared plus 2 alpha delta theta. And k-rot, rotational kinetic energy. That this is kinetic energy you have because you're moving from place to place. This is kinetic energy you have because you are rotating. And it's going to be 1/2 I omega squared. The challenge is to not freak out because they look like strange symbols. That you can do this, and you already have all the tools in hand. One more fact, if you've got something going around a circle, this little red dot's going around a circle of some radius r, and it goes through some displacement, some angular displacement, delta theta, the distance that it has gone is going to be the length of this arc, which is going to be the radius times delta theta. That's because theta, if it's measured in radians, is the ratio of this arc to this radius. And so you have this equation. And then if you divide through by time, you get from that equation to this equation, that there is this one-to-one correspondence between the angular velocity, how fast it's changing its position, and the tangential velocity that this point has here on the rim. And same, a nice translation between the tangential acceleration. You know, if it's going around in a circle, it also has a radial acceleration, a centripetal acceleration. That's not what I'm talking about. I'm talking about its acceleration tangent to the curve would be equal to the angular acceleration, the speeding up of the turning here, times the radius. I find it, I know that these equations are out there. I have a little trouble remembering them. And the way I remember them is that this is in meters and this is in radians, but radians are dimensionless. I remind you that a radian, or a rad, is equal to the length of the arc you have gone through divided by the radius. That's meters divided by meters. Radians are dimensionless. So on this side of the equation you have something with dimensions of meters, and on this side of the equation that has no dimension. So it needs the meters. Again, this is meters per second. This is radians per second. It's like nothings per second. So this side of the equation needs the meters in order for it to be meters per second on both sides. If that's helpful to you, that's great. That's how I remember who gets the R when I'm dealing with this relationship. It is a very valuable relationship for you to hold on to. Okay, so a problem. I have a wheel spinning, and What would this quantity be? What have you found there? Yes, you found omega. And just like naked velocities, this sort of looks like a little bottom, don't you think? Oh, how embarrassing! Well, you certainly won't want it to be naked. This needs to be clothed. So how are we going to clothe it? I'm anxiously trying to worry about that. What acceleration? This is going to be angular acceleration, I'm pretty sure, will be needed to stop. Oh my, they didn't run that one by me. That's going to be the final angular velocity. So this is the initial angular velocity. Oh, isn't that much more comfortable to look at? I'm not embarrassed at all anymore. In just 2 revolutions, that's going to be delta theta. There is no V. There, you see I've clothed it. Find the equation that fits these things and plug in the values. This would not be a 2 that you would put in here. How many radians is 2 revolutions? And get an answer. Switching gears, want to talk about that torque that we passed over earlier. That I have a wrench and I'm trying to make this bolt turn, trying to put a twisting force on it, what we speak of as a torque. And I have these 4. The magnitude of these are all the same, but the direction and the placement on the wrench is different, which will produce the greatest turning force for this bolt. And I hope you can agree that just from your experience as a human being living in the world using tools, that you would want to get as far away as possible. And then there's a hard choice, and I think that 3, that same force acting this way, some of the force is wasted when I go that way. If you don't buy that, try turning the force to an even steeper angle, or even this angle. And can you see that as I approach having the force act parallel to the handle, that is not going to cause it to turn at all. So I don't want my force acting parallel. It is the perpendicular part that does the torquing for me. So here you have a the torque, I hope you can agree, depends upon how far you are away from the pivot. The pivot is the point you are turning around. To get further away from the pivot is to have more torque. To apply more force is to have more torque. But I also only want the component of the torque that is perpendicular to the arm. All of these go into torque. And here is the equation. That torque is equal to the cross product. Oh my. That the arm, a vector from the pivot out to where the force acts, it does have direction. That arm is a vector quantity. And then the force, also a vector quantity. You are multiplying 2 vectors together, from which it is possible to get either a scalar or a vector. But torque is clearly a vector. You can torque it around that way, or you can torque it the other way. We'll get into the details of the direction of torque another time, but clearly torque has direction. You can loosen the mayonnaise lid or tighten it. And so instead of a dot product, a scalar product, we are going to do a vector product, which is also known as a cross product. And what we mean by a cross product is RF sine theta. Remember, for a dot product, it was RF cos theta. That this angle theta here is the angle between R and F, but to find that angle, you need to put R and F tail to tail. I need to get rid of these guys. You. No, not you. Okay, excellent. You put them together tail to tail, and this angle between them, when they are tail to tail, is what we mean by the angle between R and F. And I hope you can see that if you take the sine of theta, then that's going to be giving you the perpendicular component of this force vector. That the parallel component, of course, does not produce any torque. Done. We are done. Have a nice night.